Okay, we are done with one of the two most important concepts in the nervous system, namely the resting memory potential. The other important concept of in the nervous system is the action potential. But we'll talk about action potential probably um, on Thursday. If not, then it will be on Tuesday for sure. Now, um, before the next topic that I talk about is the something called graded membrane potential, which is the building block of action potential. But before we start the graded membrane potential, which is relatively easier to understand than the resting membrane potential, we need to define some terms. Okay, these terms are important for you to further learn about the nervous system. Many students they do not have a good understanding of these terms, and then they move on to learn about graded membrane potential and then action potential, and that mess up all their understanding. So I hope you have a clear understanding about these terms. The first one I'll talk about is called depolarization. Depolarization, I personally define it as an increase of potential, of membrane potential from RMF. So what do I mean by that? Okay. So you have the let's say you have here minus 70 millivolt in here. The y-axis is the membrane potential in terms of millivolt. Okay, so you know that you have the minus 70 here. This is your resting membrane potential. Let's say your membrane potential now increased to minus 55. We call this depolarization. Or when it increased to, let's say, plus 30, we still call this depolarization. Okay? And then the next one is called hyperpolarization. I personally define it as a decrease of membrane potential from RMF. For example, this is minus 90. So if the the cell goes from the resting membrane potential go to minus 90, we call it hyperpolarization. Now, let's take a look. The third term, we call it repolarization. For repolarization, it's basically the membrane potential return to resting membrane potential, resting membrane potential, not F. Hey, I'm sorry, misspell it. Sorry. So this is F, this is P, potential. It should be red. Okay, that is right. Not RMF. Okay, RMP, resting membrane potential. Okay. Repolarization, meaning that the membrane potential returns to our resting membrane potential. So it can be from positive or from negative. I'll show you what do I mean by that. Remember, let's say if it is plus 30. If the cell right now is at plus 30 millivolt, when it goes back to the minus 70, we call that repolarization. Or when it is at minus 50, when it goes back to the minus 70, we also call this repolarization. So as long as it returns to the resting membrane potential, we call it repolarization. Similarly, if the cell is at minus 90, and if it goes back to the resting membrane potential, we call this repolarization as well. That's why I said that it can be from positive or from negative. As long as it returns to the resting membrane potential, then we call this repolarization. Is that clear? All these terms? Well, okay. Then we'll go then we'll go to the next topic, graded membrane potential. Okay, we finished one of the two most important concepts in the nervous system, namely the resting membrane potential. The other important concept in the nervous system is called action potential. But before we go to action potential, we'll probably talk about action potential either on Thursday or next Tuesday. We will talk about something called graded membrane potential. So the logic of the lecture is like this. We first start to give you a brief overview of the functions of the nervous system, and then we give you a brief review of the anatomy of the nervous system, and then we talk about resting membrane potential, meaning that when the cell is not doing anything, resting membrane potential is like the foundation or the building block of everything. That's how we talk about resting membrane potential first. Or you may even consider resting membrane potential as the homeostasis of a neuron. You may consider resting membrane potential as the homeostatic states of a neuron. Namely, when the cell and the neuron is not doing anything, then the neuron is at homeostasis. Now, What about greater membrane potential? Greater membrane potential is when the neuron deviate from the homeostasis, but the deviation is just a little bit, okay? And what's the differences between greater membrane potential and action potential? We'll talk about later. Action potential is when the cell deviate from the homeostatic resting membrane potential a lot. When it is doing something significant, then we call it action potential. When the neuron deviate from the homeostatic resting membrane potential a little bit, then we call it greater membrane potential. And the relationship between greater membrane potential and action potential is that greater membrane potential is the building block for the action potential. It's like the relationship between the two is that resting membrane potential is like English alphabet. Greater membrane potential is like English words or vocabulary. And then action potential is like sentences. So that's why we go through this one by one in order. Now, this is a brief review of what we just learned previously. Remember, we talked about depolarization and hyperpolarization. So depolarization is here. This is an example. What is the definition of depolarization? Remember that I personally define it as an increase of the membrane potential from the resting membrane potential. The resting membrane potential is minus 70 millivolt, and it is an increase. Let me see an increase. So the increase is from here to here. So this is an increase of the membrane potential from the resting membrane potential. So that's why we call it depolarization. How do we trigger depolarization? At this stage here, you can assume that it is by stimulus. Okay, I don't want to get into too complicated and mess up your understanding. The stimulus, you may assume that it is a mild electric shock. So you can shock a neuron a little bit, then it will give you depolarization. What about hyperpolarization? Remember the definition of hyperpolarization we talked about in the previous slide? Hyperpolarization is basically a decrease of the membrane potential from the resting membrane potential. So it is here. I hope you can see it on the screen when it is bigger. So basically it's just a little drop of the resting membrane potential, and we call it hyperpolarization. It is a decrease. And the stimulus, you may also assume the stimulus is the also mild electric shock. Okay. Then you may ask me, hey, Professor, how come a mild electric shock can induce depolarization and hyperpolarization? Well, that you can assume that the mild electric shock, one is a positive mild electric shock, one is a negative mild electric shock. In this case, then you understand, oh, okay, it can induce depolarization and hyperpolarization. Depending on the polarity of the mild electric shock, then you can have two different kinds of a result. Okay. And the mild deflection, the small deflection that you see here, we call it greater membrane potential. So the small deflection here, we call them greater membrane potential. So greater membrane potential can be a depolarization or it can be a hyperpolarization. Either one as long as it is a small deflection from the resting membrane potential, we call it graded membrane potential. It's a small perturbation or small disturbances of your homeostatic resting membrane potential. We call it graded membrane potential. So, what are the characteristics or properties of graded membrane potential? Okay, graded membrane potential, sometimes we just simplify it. We just call it graded potential. It's the same thing. Graded potential, so we just simplify it, calling it graded potential, but it is the same as graded membrane potential. The first one is that, okay, graded potential directly proportional. This is a mathematical symbol, looks like a fish. Lots of students call it a fish, but it's a mathematical symbol. It means proportional. Graded membrane potential is proportional to the stimulus intensity. In this case, we call it directly proportional because what does it mean? If we look at it here, when we give a mild electric shock, okay, of course you see the weak deflection, and then if we give not a mild electric shock, if we increase the intensity of the electric shock, we give a stronger electric shock, then we'll have a higher graded membrane potential. So that's why we call it directly proportional. Okay. Because of that, we call the we call graded response. We call this a graded response. Graded response meaning that the amplitude of the graded potential, the amplitude here and here, will change according to the intensity of the stimulus. If you give a stronger electric shock, then you will have a higher amplitude. That's basically it. Graded response. The amplitude of the graded potential will change according to the stimulus intensity. That's why I call this directly proportional. Number 2, graded potential is again this symbol, but here it is 1 over distance. For properties number 1, we call it directly proportional. Property number 2, we call it inversely proportional. Meaning that if the distance increase, then the graded potential decrease. What do I mean by that? So here you can just erase that, forget about this part. Okay, don't need to know about this. This is bad. So what happened is that when you give a stimulus here, so now the x-axis is the distance. X-axis here is the distance. So if you give a stimulus, let's say it is an axon. Okay, this is an axon, a very long axon here. So if you give a stimulus at the beginning of the axon that I highlighted in yellow with yellow, and then you measure the deflection like immediately after the site of stimulation, then you see this deflection here. And then you measure the response 1 millimeter away from the site of stimulation. That means here to here is approximately 1 millimeter. And then you measure the graded potential. It actually becomes much shorter, much lower. We call it decremental response. Decremental response. Decremental response, meaning that graded potential will decrease, it will lose. If you measure it another millimeter later, what will happen? What would you see? You will see nothing, because at that distance everything will be so-called degraded. That's why I call it decremental. This is what we mean inversely proportional. The graded potential will be the highest next to the site of the stimulation. If you measure the graded potential farther away from the site of stimulation, then it will become smaller. If it is further away, then it will actually disappear. Okay, this is what we mean in the properties number 2. Graded potential is inversely proportional to the distance. The longer the distance, the smaller the graded potential. The shorter the distance, the larger the graded potential. Now number 3, summation. Summation, you have 2 types. One is called temporal, one is called spatial. You have 2 types of summation, temporal summation and spatial summation. So let's take a look at temporal summation first, which is in here. So let's say you give a mild electric shock at this point, okay, at this time x, okay, no, x is basically the amplitude, the intensity, the stimulus intensity. Okay, the stimulus intensity is x value. You give a mild electric shock to the neuron, and then it gives you the small depolarization. Okay, so that it will be a graded potential here. And then after this, it will go back to the resting membrane potential. Nothing special here. But what if we give 3 consecutive mild electric shock, and the time in between them, they are very, very short, very, very close to each other? What will happen? So the first one you will see, the first one here, the stimulus here, you will see, it will give you this graded membrane potential. Originally, it should go like this. Originally, Before the graded membrane potential disappear, you give another shock. You give another shock here. You give another shock, then the second shock will produce a graded potential on top of the first one. Okay, and then it should dies down like this. But before the second one dies down, then guess what? You give a third stimulation before this at the peak of the second one, so that you have this one here. In other words, these three graded potential, they build on each other. How can they do that? Based on the time that you give the stimulus. Based on the time you give the stimulation. The time has to be very short so that the membrane potential can build on each other before they die. Okay? And when you give three stimulation of the same intensity, they all have the X intensity. They all have the same intensity X. They all have the same intensity X, but we stimulate them very with a very short interval, then the graded potential can build on each other so that you get one gigantic graded potential. This is what we call temporal summation. Temporal means time. What do I mean by time? It is the stimulus interval. The interval between the stimulus, they have a very short time. Because of the short time between the stimulus, then the graded potential can build on each other. This is what we call temporal summation. Spatial summation is a little bit, I need to draw a picture, okay? I hope you won't laugh at my drawings, okay? Okay, this is a neuron. Okay, these are the dendritic branches. Okay, now let's give them an electric shock. Let me give a mild electric shock at this end here. A mild electric shock at this end. When I give a mild electric shock at this end, what would you get? Okay, I'll get a graded potential. The graded potential will go this way. Okay, is that clear? Let's say I give a mild electric shock at this point here. And then I'll get another graded potential here. And the graded potential will go this way. And the two mild electric shock, they are of the same intensity, okay? It's the same intensity. But it's just that I apply them at a different dendrite. So the dendrite here, I call this dendrite X, and then I call this dendrite Y. But the intensity, they're the same. So the amplitude of this graded potential should be the same as the amplitude of this graded potential here. So they should have the same amplitude, the same height. And guess what? When they reach here, what will happen? When the two graded potential reach the soma will add them up. And then they will become taller. If the amplitude here is, let's say 1, amplitude here is 1 because they are the same intensity, so they give you the same amplitude. Here, the amplitude will be what? You probably know the answer. Will be 2. 1 plus 1 equal to 2. So it will add up and become higher. This is what we call spatial summation. If you stimulate a different dendrite with the same intensity, dendrite X and dendrite Y with the same intensity, so you induce the same graded potential at different dendrite. When they travel the same distance and reach the soma at the same time, the soma will add them up to form a bigger graded potential. We call this temporal summation. We call it spatial summation. Sorry. Spatial summation. Spatial summation means space. The summation require the location. Depends on the location. That's why in here X, the stimulus here stimulate at the dendrite X, the stimulus here stimulate at the dendrite Y, but they are of the same intensity because you can see that the amplitude of the graded potential, they are the same height. And then after you add them up in the soma, then the amplitude double. We call this spatial summation. Is that clear? All right. So that's all. We will end here. Okay. It's approximately the end of the class. So next time on Thursday we'll talk about action potential. Okay. See you all on Thursday.